In this lecture, we'll look at potential energy stored in the inductor. And specifically, we're still looking at the solenoid. And so what we have is, we have the inductor here. And in this inductor, there's magnetic field. We're going to say that there's a magnetic field in this thing, B. And of course, that means that there's some kind of a current I flowing through this whole system. So we have current flowing through the inductor, and there's a magnetic field stored in the inductor. And in the magnetic field, there's energy stored in all, whether it's gravitational or electric or magnetic field. Every field stores energy. And specifically, there's energy here in the magnetic field, because if you start losing this magnetic field, let's say you start with just the solenoid, and somehow you manage to set up a magnetic field here. So there's magnetic field B, but you turn off the current. So there's no current, you just have magnetic field. Well, if there's no current, then the magnetic field will start to decrease. And as it decreases, changing magnetic field will force the charges to flow. And so you end up with kinetic energy in the flowing charges. But that energy must come from somewhere, and it comes from the magnetic field while it's being collapsed. The energy from the collapsing magnetic field is transferred into the kinetic energy of the charges as they flow. So you end up with charges moving. So there must be energy stored in the magnetic field, right? And so let's see if we could figure this out. So we'll do it this way. Power is the rate at which energy is lost or gained, so the EDT. And specifically here, we're looking at the energy stored in the magnetic field. So I'm going to rewrite this as power of the magnetic field would be ddt of the energy stored in the magnetic field. And power of an electrical component in a DC circuit is defined as voltage across that component times the current. This is by definition power. And there's some voltage here, delta VL. So if we're looking at an inductor, then I'm going to put VL here. And then what I can do is I can just write this as voltage across the inductor times the current through the inductor, dt equals d of the potential energy in the magnetic field. And now I can integrate. So what I'll have is, I guess I can take one more step. The voltage across the inductor is going to be, the magnitude of that voltage is going to be L times di dt. dt equals d of the potential energy stored in the magnetic field, and that allows me to get rid of this piece. Oh, that's right, I'm missing something. I need to have I in here. This I is what I forgot to write here. And so now what I'm going to have is, I'm going to integrate. And on the left hand side, what I'll get is L is a constant that comes out, I di, and I'm going from some zero current to some maximum current. And on the other side, I'm going to have, I go from some zero potential energy to some potential energy, right? So I'm going to go from 0 to some final potential energy associated with the maximum current. This is d of the potential energy stored in the magnetic field. And so now I can bring this, actually let's take another step. So what I get is a half Li squared equals the potential energy stored in the B field of solenoid. So this is the equation for energy of an inductor. So energy in the inductor. And on the worksheet, you have a few problems that you can try with this equation. And then another thing that you have is energy density. So energy density in the inductor or in the magnetic field B. So what we'll do is we'll call this U, since this is what your textbook uses. So U equals, and then energy density would be just energy per volume. And so what we'll say is that the picture that we have is that the magnetic field in the conductor points like this, and then the volume of the inductor is just the volume of the cylinder. And then the volume of a cylinder, well, that's just pi r squared times the length of the cylinder. Maybe I should use lowercase l. So L, that's the length of the cylinder, and then R is just the radius. So this equation here then becomes half L I squared divided by pi r squared times L. And so the energy density U equals half, comes out L. Well, that would be the inductance of the inductor of a solenoid. And probably add loops. And so the inductance of a solenoid, that was, let me look this up because I don't remember that expression. It's mu naught times n squared, the number of loops, times the area of an individual loop, which is pi r squared, over the length of the solenoid, that was L, the inductance. Then I have times I squared divided by pi r squared times L. And so this goes away. L gets squared. And so I have here U equals half mu naught times n squared I squared over L squared. Now, magnetic field of a solenoid is mu naught times I n number of loops over L, I think is what it was. And so then I can rewrite this as B times L over mu naught times N is I. I can take this expression and plug it into this expression for the energy density. And so I have U equals half mu naught times N squared over L squared times I. And so we get here B squared times L squared over mu naught squared times N squared. So I'll try to separate this. So N goes, L goes, part of this thing goes, and I end up with U equals a half B squared over mu naught, energy density in the inductor of a solenoid. It turns out that even though we use the specific example here of a solenoid, it turns out that this is true in general. That is, if you have a magnetic field, and let's say the magnetic field points like this, so something like that, here's the magnetic field, the energy density, or Teslas per meters cubed, it can always be calculated using this equation. So as long as you know the magnetic field, the value of the magnetic field, you can easily calculate the energy stored in that field in every cubic meters. As a reference point, somewhat of a reference point, this is the energy density of the magnetic field. Energy density of the electric field was similar. It was 1/2 epsilon naught times E squared. As long as you knew the electric field at any space, any point in space, if you know electric field, and you can square it, and you can figure out how much energy you can pack per meter cubed. So now suppose that we have a situation where we have both electric and magnetic fields present in the picture. So maybe we have a capacitor where you have a plate, one plate, so maybe some kind of a circular plate this time for a change, and you have another plate, here's a circular plate. And then you keep packing charge on this plate. So plus, 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 and the charge keeps increasing. You charge this capacitor minus, 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 and charge keeps increasing. You're charging a capacitor. In that case, there's an electric field here. And it's not just that there's an electric field, but this electric field is increasing. So you have electric field, which is increasing. And if you have an electric field that is increasing, then you know that you're going to also have a magnetic field around this electric field here, Faraday's law. And so there would be a magnetic field that'd be circular here. There's also a B field. present. So how would you calculate energy density if you had both electric and magnetic fields present? Or what if you just had an electromagnetic wave, so that you have an electric field that does something like this? That'd be the electric field. And then you have a magnetic field that does something like this, and maybe I'll put some vectors here to indicate that what we have are vector fields. So perhaps you're looking at light that travels to the right at some speed v, which would be in fact the speed of light c. But anyways, how would you calculate the energy density if you had both electric and magnetic fields present? And often enough they are both present there. So then you do U total equals energy density of the electric field plus energy density of the magnetic field. And you just, well, let's do it. So we would have half epsilon naught times the electric field squared plus half magnetic field over mu naught. And then you have to use the following. Electric field is C times B. We never derived this expression, but it can be derived. And also C equals 1 over, speed of light is 1 over mu naught times epsilon naught. Comes out of Maxwell's equations. Both of these expressions come out of Maxwell's equations. And so now you can use them and put them into this expression here. So the total energy density in a case where you have both electric and magnetic field present are, well, let's get rid of the magnetic field here in this expression. So half, and I have epsilon naught times E squared plus 1 over mu naught times B. But instead of B, I'm going to make some room here. Let's put this thing somewhere out here. What do I have there? Magnetic field squared, B squared. So instead of B squared, I'm going to have E squared over C squared, but C squared is 1 over mu naught times epsilon naught. And so in that case, what I can see here is that this nicely cancels out and the other thing comes back up. So then the energy density, total energy density would be half epsilon naught times the electric field magnitude of the electric field squared times, plus epsilon naught times E squared. And now I have my expression for total energy density, which would be epsilon naught E squared. And of course I could derive something similar in terms of the magnetic field, but there's that. So if you had to calculate energy density in a case where you have both the electric and magnetic fields present in certain space and one field arises out of the other, then you could use this equation here on the bottom. All right, units would be joules per meters cubed.